Ladies and gents, thank you for joining us for this week's Geotalk. We are nearing the end of the first semester's Geotalk series, so thank you for joining us. We're going to have a few more talks in June, and then we'll take a break in July for a month during our field trip season. But thank you for joining us today, and special thanks to Dr. Stacia Gordon for joining us all the way from the University of Nevada, Reno, where she's an associate professor, mainly studying thermal, rheologic, and chemical changes that occur as a result of plate tectonic processes. And as you heard today, she's particularly interested in ultra-high pressure conditions and the role of partial melting. So Stacia, it's wonderful to welcome you to this Geotalk. Stacia got her PhD in 2009 from the University of Minnesota, and then spent several years at the University of California in Santa Barbara, working as a postdoc and a researcher there. So thank you, Stacia, for joining us, and thank you, Linda Cherry, for setting up this talk. Much appreciated, and thank you to the audience for joining us from all over South Africa, and I think there's some international folk as well. So thank you very much to those of you on Zoom and of course on YouTube as well. We hope you enjoyed this talk, and Stacia, over to you, and thank you so much.
All right. Well, thank you both to Linda and Grant for organizing this. Let me just get back to my video. Okay.
There we go. You can see your screen.
Well, thanks. Perfect. Well, thanks again for inviting me. And again, I feel like this is one of the few advantages of the pandemic, of being able to interact more easily internationally. And so today I want to share some of my research on some of the Earth's youngest known ultra high pressure rocks, and looking at their tectonic history of how these crustal rocks went from the mantle to the near surface in less than 3 million years or so. And one thing before I start, I just really need to point out that this is a huge collaborative effort, and that's one of the fun parts about this project is it's involved a large group of scientists. And I'll be featuring a lot of work of my former PhD student, Joel DeZormo, and we continue to collaborate on these rocks, as well as Tim Little and many others. In addition, really have to say that this work was only possible to the funding from the National Science Foundation in the US, as well as Marsden funding from the New Zealand government. So just to begin, start out in a very basic subduction zone system, and one that we see in kind of our 101 geology textbooks. And so I think we're all familiar with this, but just the idea that we know that we have crustal material, whether it be oceanic or at some certain times continental crust, that's carried down deep into the earth. And we know that sediment along, in this case, this oceanic crust, will undergo a variety of different metamorphic reactions, producing rock types such as serpentinite, and at increasingly higher pressure conditions, blue schists and eclogite at the greatest depths. And that these metamorphic reactions that are occurring not only consume, but also produce a variety of fluids and potentially melts. And that's illustrated within this little simplified diagram, at least some of these fluids coming off of and rising off of the plate by these blue arrows, and going into the mantle wedge, where we know it causes partial melting and ultimately leads to arc magnetism. And so these reactions, as well as the transfer of material through the subduction system, has really profound geochemical, as well as geodynamic effects on this entire system. And so just thinking about kind of different processes of mass transfer, metasomatism, all of this can lead to rheological changes of this environment and kind of how the crust is evolving within this overriding plate. And just to give a couple of examples of what I mean by these different processes of thinking about mass transfer and cycling within this system, here's an example from Planck and Langmuir, where they focused on element recycling within the subduction factory, where they looked at different areas around the world and looked at the composition of the sediment going into the trench and compared it to the composition of the magmas and lavas coming out at the volcanic front. And here's examples for potassium, barium, strontium, and thorium, where on the x-axis, we're looking at the composition of those elements within the sediment, and then comparing it to the same elements on the y-axis in the lavas. And what you can see is that there's a really direct correlation. And so in this study, as well as in many studies subsequently, they've really shown that you have efficient large-scale recycling through the subduction factory. And this can have big influences on how the Earth has evolved geochemically, also thinking about crustal differentiation and the formation of the crust within the subduction factory. And then just an example of potential rheological effects, turning now to a thermomechanical numerical modeling study up on the top, and then kind of some of the interpretations in a cartoon on the bottom of the slide. What this study focused on is what happens when that subducting plate gets to pressure temperature conditions where it can undergo partial melting. And so that's what these percentages are, and the kind of where the slab is going white to the pale pink is where we're starting to get partial melt. And we know that once partial melt is present, it's going to significantly weaken the crustal material. In addition, it's going to be quite buoyant and want to potentially rise up towards the surface, in particular, in comparison to mantle conditions or mantle densities. And so this can have major effects on that overriding plate and lead to potentially crustal flow and crustal thickening within that overriding plate. And so it's important to kind of think about how the rheology is changing and potentially if we do have partial melt present within the system. And with all of these processes, we also have to think about timescales because they're all occurring on quite different timescales, or many of them are occurring on different timescales within this factory. And so to be able to look at kind of the consequences of different processes, we also need to know the timing as well as how long they're lasting. And just examples of thinking of this partial melting and how the slabs are changing and ductile flow. This is occurring on the tens of millions of years versus if we jump up into the Arc volcano that's part of this system. And here's an example from Mount St. Helens in Washington by Pallister et al. In 2008, where if we go into the magma chamber, here we have magma resonance times on the tens of thousands of years. And so in this study, I'll use a lot of geochronology to kind of try to walk through the history and tectonic evolution of UHP rocks found within Papua New Guinea. And so to be able to study these processes and kind of understand how material is moving from deep within the earth, or crustal rocks, I should say, in particular, and up to the surface, we need to have access to the rocks that have experienced these conditions. And we can't exactly go down along a subduction zone to collect samples. And so instead, that's where these ultra high pressure terranes provide a unique window into what's happening within this subduction zone environment, and in particular into the metamorphic reactions and associated fluids and melts. And so here's examples of kind of all the known or major known UHP terranes on Earth. They're color coded by how deep the crustal rocks were subducted to or buried to, with yellow representing around 60 kilometers. Red is where quartz has transitioned into coesite, which is typically occurring around 100 kilometer depths, and then graphite into diamond at 150, and then the presence of majorite indicating subduction down to 200 kilometers depth. And so in general, most of these ultra high pressure terranes record fairly similar pressure temperature conditions. So just a PT diagram shown here with many of the major UHP terranes shown on the diagram, where most of them achieved pressures of around 3 GPa, again, representing that around 100 kilometers depth, and temperatures from around 600 to 800 degrees C. So relatively cold in comparison to the depth. And this is consistent with this yellow box is showing us what most models predict for steady state subduction of oceanic crust. And there are a few examples that got to much higher temperatures and kind of mantle wedge type conditions, but those are quite rare. And most of them are in that kind of window of our steady state subduction of oceanic crust. And then just in general, how do you actually get these crustal rocks back up to the surface? Because we know that as they're being subducted, they're undergoing metamorphic reactions that are causing their density to increase. But in general, they're still mostly less dense than the surrounding asthenosphere. And that's because most of these ultra high pressure terranes are about 95% quartzo-feldspathic gneiss and only about 5% mafic material. And so buoyancy is on their side. So in general, here's two cartoon examples from Hacker 2007. We have some sort of slab breakoff event releasing that anchor. And then in some cases, the ultra high pressure rocks come up as a more coherent slab up to the surface. And this is observed in some of the larger ultra high pressure terranes on Earth in places like the Western Gneiss region in Norway or in Dabi Sulu in China. In other cases, when that slab breakoff occurs, these ultra high pressure rocks come up in smaller kind of more Rayleigh-Taylor instabilities or diapirs that rise up to the surface. In both cases, the rocks typically follow a near isothermal decompression path, which results in partial melting during exhumation. And that's what's indicated by these little teardrop shapes. And so today I want to focus in on these really young ultra high pressure rocks found in Papua New Guinea. And some of the questions we've been focusing on in this study is overall just trying to unravel how these rocks got to the surface and what that exhumation path looked like and what was driving that exhumation. But first we'll walk through what rocks were actually subducted to the mantle depths, at what pressures and temperatures did these rocks equilibrate in terms of their peak conditions, and then what was the timing of the UHP metamorphism as well as melting that occurred at great depths and during exhumation, and then how exactly were these rocks exhumed. And so jumping into the overall tectonic environment, we're looking at what I think of as kind of a bird flying to the west of this island of it's a combination of partly Indonesia and Papua New Guinea, where Papua New Guinea is found in kind of the bird's tail, if you will. And so this overall island is found north of kind of central to eastern Australia. On the bigger map, we're looking at the overall tectonic setting where it's dominated by the convergence of the Australian plate in the south with the Pacific plate in the north. But in between these large plates, there's a number of smaller microplates that are shown here, such as the North Bismarck plate, South Bismarck, as well as the Woodlark plate. And so these plates are very rapidly moving around and rotating, and so creating a very active tectonic setting. So we're going to zoom in now onto the easternmost part of the Papuan Peninsula and into this area of the Woodlark plate. And so in this area, what we have is that the Woodlark plate is actively subducting along this New Britain Trench in the north. And that's actually causing the counterclockwise rotation of the plate. You can see that really nicely in the inset showing geodetic data from the region and those clear clockwise rotation shown in those arrows. And this rotation is actually causing the seafloor to rip open within this Woodlark basin. And so we have seafloor spreading that began about 6 million years ago in the eastern part here, and it's propagating towards the west where it transitions into continental rifting right in this area of the D'Entrecasteaux Islands. And this is where the ultra high pressure rocks are found that I'll be discussing today. And so we're within this very active tectonic environment with lots of extension going on. So it's a bit of a unique setting compared to many of the other ultra high pressure terranes on Earth. But it also makes it for a really exciting place to study because there's so many different kind of geologic fundamental processes happening here. So in terms of the rocks and what they represent and what the sediment was before it was subjected to these great depths, if we step back into the Paleogene, this is kind of a cartoon cross-section showing what was going on during that time, going from the southwest to the northeast. During that time, the Australian plate was subducting to the north. And it actually collided with a island arc at around 58 MA, and this is based on dating the metamorphic soul, because partly what happened during this collision was that some of the basement of this island arc was actually abducted onto the continent. And so that's what's called the Papuan ultramafic belt that's shown in this lower image. And so we know that this happened sometime between 58 and then continued that collision until 22 MA, just based on sediment found in basins related to this collision. And so we believe that some of the Australian kind of margin sediments were what were subducted down during this time to form the ultra high pressure rocks that we see today. So in terms of that collision, this Owen Stanley fault zone that's represented by the red line here is actually the suture between that collision. So rocks to the south of that are all part of the Australian plate. And to the north of that is where we had the Papuan ultramafic belt that kind of blanketed this entire area. And some of it is still found on the D'Entrecasteaux Islands today. So we're going to zoom in on this box here onto the islands now. And just a simplified geologic map of the islands. And the ultra high pressure rocks are found within multiple domal structures that are represented by mainly these greenish colors. They're bounded by high angle normal faults that are the black lines, and these overprint what were once low angle normal faults. And the hanging wall of the normal faults in purple here are some of that Papuan ultramafic belt, so some of the basement of the island arc that was abducted. But then as you go into the footwall of the island arcs, this is where, of the domal structures, this is where we have these ultra high pressure rocks. And they've been classically divided into two main zones, a carapace versus a core zone. And this is mainly describing the fabrics that are observed, where the carapace rocks in the lighter green are structurally higher. They were more affected by the detachment faulting. And so overall, they have a much more planar fabrics that you can hopefully see in the lower left image, versus as you go structurally deeper into the dome, into the darker green units, we see that the fabric becomes much more chaotic. At all structural levels, there's lots of evidence of partial melting in this white layers or leucocratic material. And overall, that partial melt or amount of leucocratic material increases in terms of volume percentages as you go structurally deeper. The other thing to note is that all structural levels, you do find evidence of mafic blocks within mostly quartzo-feldspathic gneiss, and some of them preserve really fresh eclogite facies, assemblages, and but many of them have undergone retrogression. And so in terms of why we were interested in studying this area, one of the things that was really intriguing about the PNG UHP terrain is that it arguably exposes the greatest amount of crystallized melts of any of these ultra high pressure terrains on Earth. And so here's a picture of a classic outcrop there, where you can see that there's multiple generations of melt represented within this outcrop, where in the bottom here, kind of below one of our guides' foots here, you can see that there's some leucocratic material that's really strongly deformed and foliation parallel, and that's clearly cut by multiple other generations of melts, including, here's a very retrogressed mafic Goodenough pod within here that's been totally cut and by leucosome. And so, as I mentioned earlier, we know that once partial melt is present, it's really going to change the rheology of the rocks, and also really increase the buoyancy. And so part of the goal is to understand the role of the partial melting in exhuming these rocks to the surface. The other intriguing part about this, as I mentioned, is just that it's in this very active extensional environment. The excuse me, geomorphology is quite incredible, just beautiful flat irons showing those high angle and normal faults that bound the domal structures. And so everything in the going towards the interior of the island would be the ultra high pressure rocks. And again, these are cutting what were once probably more lower angle normal faults that helped in exhuming the UHP rocks to the surface. The area in general is also very still undergoing very rapid uplift. And you can see that very clearly in a variety of uplifted reefs that are found as you're cruising around these islands, and just a canoe for scale in the lower image. And this is one of the ways that we kind of explain our work to the local people, because I have to say many of the local people are quite suspicious of us when we arrive on the islands. And I think a lot of mining companies have come in and taken out a lot of materials from these islands and have not really respected a lot of the local people there. And so they're quite suspicious of geologists and assume that we're coming in to steal gold and silver. And so we spend a lot of time trying to explain our project. And this is one thing that helps us is the local people understand that the reefs form within the ocean. And so we can kind of point to these reefs being uplifted to explain that this is what we're trying to study is how the earth is changing in both horizontal movements where a colleague was doing geodetic work, and then also these vertical movements. And just one more picture of the geomorphology, where you can see here kind of multiple fluvial terraces, again, suggesting repeated river incision and rapid uplift within this area. So this very active tectonic environment for a UHP terrain. And then one other kind of final interesting part of the geology there, going to some of the geophysics work by Jeff Abers, and this one published back in 2002, where he was looking at the depth of the moho throughout the entire area. So the D'Entrecasteaux Islands shown in kind of the middle here, the Papuan mainland towards the southwestern corner, and then the Trobriand Islands in the north. And what he found is that the moho or the crust is quite thin within the area of the D'Entrecasteaux Islands, and essentially where you have continental rifting, and thicker as you go out from there. And this isn't too surprising because you're in this area of extension, but hopefully what you saw in a lot of the photos is that there is quite high topography on these islands. And so in terms of trying to explain how you can have this high topography while also having a thin crust, he turned on looking at what was happening in the mantle. And so what's shown in the red to blue are mantle velocities. And in this area of the islands and within their overall rift zone, he showed that you have these anonymously low mantle velocities. And so argued that you have lots of extension happening at mantle depths, and essentially the mantle coming in and filling in below these islands to support that high topography. And so overall, I know I've just thrown a lot of information at you. So this is a bit of a summary slide in a cross section going through one of these domes from south to north. And in the south, we're essentially at the mainland, and then one of the domes on the Goodenough Island in the west, and then going out to the north from there. And so overall, again, we have these domal structures that are currently cut by high angle normal faults. In the footwall of those faults is where we have these ultra high pressure rocks, and the entire system is essentially supported by mantle that's come in and kind of sitting directly below it. Okay, so jumping into our work within the islands, one of our goals was we wanted to compare what's happening across multiple domes. And so we did collect samples from all three of the domes shown here of Goodenough in the west, and then Mailolo and Oyutabu on the Ferguson Island. And the first thing we wanted to look at was really trying to understand their pressure temperature history. And we weren't the first people to work on the PT results in this area. And so Suzanne Baldwin was the pioneer within this area and continues to publish a lot of interesting studies from here. And her group was the first to discover coesite within one of the eclogite samples that currently is the only coesite that's been found within this area. And she did some dating of that particular eclogite, and that's what's shown in the left here, and found an age of 8 MA for what she interpreted as the timing of the UHP metamorphism, and then put together an overall pressure temperature path that's shown on the right here. The one thing to note, though, is that both for the age as well as the PT path is that they have really large error bars. And so we wanted to try to kind of narrow that down to better understand the history, and then look at samples from the other domes as well, to see if they all share the same history. So we collected samples. One of the challenging things in Papua New Guinea and in many of the ultra high pressure terrains is that the rocks have typically undergone a lot of retrogression during exhumation. So there's very few fresh eclogites to be found. An example on the left here is from the coesite location and showing the most fresh eclogite that we found, and I think that Suzanne's group has found as well. And then a backscatter image of it in the bottom left. And so not surprisingly, the sample consists of garnet, which is the brighter gray, a lot of omphacite, that sodium-rich pyroxene, as well as things like phengite and rutile. And what you see a lot in this sample and in many of the samples is that anywhere that quartz is included within garnet, that there's radial fractures coming out from that quartz. And that's an indication that the quartz was likely once coesite and then retrogressed into quartz during exhumation. So there's lots of evidence that all of these rocks were at these ultra high pressure conditions. Most of the eclogites look more like the one on the right, with Joel here, where we were trying to sample this thing. I can tell you we ruined at least one hammer trying to knock out a sample of this eclogite. And then the backscatter image of that eclogite below, where you can see there's still some garnet and omphacite in here, but hopefully you can see that it just looks kind of scuzzy and the garnet looks very unhappy. And that's because it's breaking down into a lot of symplectitic material, really fine wormy intergrowths of amphibole and plagioclase, as well as augite or a lower pressure pyroxene. So luckily though, you can still get a lot of information out of these retrogressed samples too. So in terms of trying to go after and understand more about the PT history, we did a combination of full EDS scans across thin sections to map out the mineral assemblage and trying to get at volume percentages of phases to calculate bulk compositions, a lot of petrography work, and then finally electron microprobe measurements of various phases to get at the mineral chemistry. And so we'll start here with the one locality where there's coesite. And I'm not sure if you can see on this map, there's a little dot right where the mouse cursor is, that's just south of kind of the main part of the Mailolo Dome. That's where the coesite is found. It's pretty incredible that Suzanne and her group found it, this tiny, tiny island. And so we went and did some more work on this at this coesite eclogite and did some pseudosection phase equilibria forward modeling using the program Perplex. And so with this, you're using a bulk composition, and in this case, what's called an effective bulk composition, where we've tried to determine what we think the bulk composition was before any retrogression occurred. And then using the thermodynamics software, you're able to produce a diagram that looks like this, where we're looking at pressure, temperature, space, and looking at which phases or phase assemblages would be in equilibrium at different PT conditions. We can then compare the mineral assemblage to what we observe in the rock and find that it fits within kind of this red box over here. From there, we can also model what compositions of phases are stable at different PT conditions. And so here looking at a combination of the end members of garnet, as well as the silicon content of phengite and the jadeite component of the omphacite. And looking at those and what was measured within our rock, all of them intersect within this area at around 28 kilobars and about 600 degrees C. And so kind of telling us that that was likely the PT conditions at which these rocks equilibrated. And so right at the transition where quartz is transforming into coesite. And just to verify that we felt pretty good about these results, you can also look at the modal volume percentages of phases within this area and compare it to what's observed in the rock. And it was very consistent with our rock assemblage too. So we feel like we really nailed it in terms of determining the PT conditions. The next part was to determine the timing and when these rocks were at these UHP conditions. And because this was such a young UHP terrain, we turned to using chemical abrasion ID TIMS geochronology so that we can get the most high precision results. For this, we focused on the mineral zircon. And for TIMS work, we do have to dissolve the crystal, put it through a series of chemical columns to allow us to isolate the uranium and lead that then gets deposited onto uranium filament. And here's our sample within the pipette. And then that goes into our mass spectrometer where it's heated up to allow these isotopes to ionize, and we're able to measure them. And so here's the results from the coesite eclogite in a standard Concordia diagram, which with each one of these ellipses representing a single zircon that was analyzed. And so all of these zircons seem to have grown from between 6 to 5.2 MA. One of the challenging things with zircon, of course, can be trying to understand what it's actually recording. And one thing that helped us with this to really feel confident that these zircons were recording the ultra high pressure metamorphism was that the zircons actually contained inclusions of the peak mineral assemblage. So things like garnets as well as omphacite, and rutile was found within them as well. And some of these inclusions were large enough to measure or analyze with an electron microprobe. And so Joel actually did that in the diagrams on the right here. We're comparing the composition of the garnet and the omphacite within the inclusion compared to that within the matrix that was used in our PT calculations. And you can see that they're exactly the same. And so we feel pretty confident that these zircons are recording that UHP metamorphism. And so the metamorphism lasted until about 5.2 MA. From the other islands and other domes, we were only able to work with retrogress eclogites, but they can still give us a lot of useful information. Here's another pseudosection diagram where I've left off the mineral assemblages, but just showing the end member compositions and where they intersect. And so again, telling us that these rocks also achieved similar PT conditions, slightly higher temperatures, but pressures kind of right along where that quartz is transitioning into coesite. And one of the advantages of the retrogress rocks is that you can also start to model when the retrogress phases are starting to appear, which allows us to then kind of start to draw in our pressure temperature path. We also looked at zircon and a variety of these retrogress phases from different domes. And here's all the results shown in the Concordia diagram in the upper right, where you can see several of the samples give really tight results from 4.6 down to about 4.3 MA. And then in the Goodenough dome in the west, all of the zircons cluster between 2.9 to 2.6 MA. And then in terms of the textural location within the rocks, here's some backscatter images on the bottom part of the screen. All of the zircons in these retrogress samples are associated with retrogression phases. So things like amphibole and plagioclase that are forming along the grain boundary of garnet. You can see it really nicely and sitting right within one of the symplectite assemblages in another eclogite. And then in the Goodenough dome, where we actually don't observe any omphacite in these rocks, and they seem to be entirely garnet and phibolites, you see that zircon right within one of the larger amphibole crystals. And so when we looked at this textural setting, we just assumed that these zircons must be recording part of the exhumation path and didn't actually grow at the UHP conditions, but later as these rocks were starting to be exhumed. And so kind of telling us and filling in what that path must have looked like and adding some timing estimates to it. However, we were still kind of intrigued by these rocks and wanted to get further information out of them about not only their peak temperatures, but also the temperatures at which those zircons grew. And so we turned to using some of the trace element thermometers that have become quite popular in the last, 10 years or so, or 15 years. And so to look at the peak temperatures, we measured zirconium and rutile. And then to look at when the zircon grew, the temperatures, we used titanium within that zircon. And here's the results from the easternmost domes. And what was interesting within these samples is that the rutile showed more consistent temperatures around 780 degrees, but then the zircon yielded actually more scattered temperatures, but many of the zircons actually yielded higher temperatures. And this is observed in another ultra high pressure terrane in China. And the other thing we noticed with these zircons is they also had large inclusions within them. And when we zoom in on those inclusions, we find that they're actually polyphase solid inclusions that consist commonly of assemblages of quartz as well as plagioclase and potassium feldspar. And so essentially they're a composition that likely represents a granitic melt. And so we think that these zircons actually crystallized out of the melt and preserved these little tiny nanogranites within the grains. And so this is quite exciting because we knew from the host quartzo-feldspathic gneisses that they had undergone partial melting, but this was really the first evidence that the mafic rocks, the eclogites, also underwent melting as well. And so we think that the higher titanium and zircon temperatures that I showed in the previous slide are indicating that you likely had an increase in temperature as these rocks were being exhumed. And that's when our partial melting occurred during the exhumation. And so, yeah, from the easternmost domes, we see this evidence. The westernmost dome, a Goodenough, seems to be on its own kind of different trajectory in terms of its tectonic history. Here's the rutile results, giving temperatures of almost up to 900 degrees from some of the rutile, versus the titanium and zircon temperatures are much lower. We also don't see any evidence of the nanogranites within these zircons. And overall, it just seems like these rocks achieved higher temperatures than the easternmost domes, but lower pressures. And so there's something different going on in this dome that we're still trying to figure out and work itself out in terms of the history. So more to come on the Goodenough dome. One thing that was notable for all of the domes is when we look at the rare earth elements for the zircons, what we find is that there is either no negative europium anomaly or a very weak europium anomaly. And then in terms of the heavy rare earth element slope, it's either flat to slightly negative. And so this is indicating that all of these zircons grew when plagioclase was unstable and garnet was stable, so indicating high pressure eclogite facies conditions. And so telling us for those easternmost domes that partial melting did occur very early on during the exhumation when these rocks were still at very high pressure conditions. And so we can now put together all of this information into this PT path, where we know that these rocks were at the peak PT conditions until about 5.2 MA. They then started to be exhumed, and along this early exhumation path, they likely crossed over these reaction lines that are telling us where phengite is likely to break down, and that's inducing the partial melting that we believe is trapped within those 4.6 to 4.3 MA zircons. And then in terms of the Goodenough samples, they're equilibrating probably more right along kind of the edge of this eclogite facies stability field at 2.8 to 2.6 MA. And then just one more little bit on these zircons, because they're just so fascinating and contain so much unique information, is we also measured oxygen isotopes from all of the different eclogites, from the coesite eclogite to the ones that contain the nanogranites, to the Goodenough one that seem to equilibrate at different conditions. And all of the oxygen isotopes are essentially the same or within uncertainty of each other. And so to me, this really argues that this UHP terrane, even though it's in different domes, but that it remained a relatively closed system during that entire exhumation history. So to summarize, the mafic rocks within these domes really provide a lot of information about the depth and conditions at which these crustal rocks were subducted to or buried to. And then they would give us some initial information about that early exhumation path to the surface. But to understand the rest of that exhumation, we're going to turn to the quartz feldspathic gneisses, and specifically to the different melt generations. And here we collected a variety of samples and are using these different melt generations to understand the deformation history, where the earliest melt generations tend to be super strongly or intensely deformed. They're layer parallel, versus some of the ones that kind of intruded into the rocks in a more intermediate time. Are an example like this, where it's a dike, but it's still folded. And then there's some dikes as well as larger granitic bodies or granodioritic bodies that intruded very late in the history and are completely non-deformed. And so these can tell us kind of about when these rocks were being exhumed, as well as when they were in place and within these domal structures. And so we collected samples from the different domes to date, and just all the results from the Mailolo dome from a variety of samples shown here, where we saw three main populations from 3.5 down to about 2.5 MA. And just to give you a sense of what these ages mean in terms of rock types, the 3.5 to 3.0 MA dates were from the strongly deformed leucozones and telling us when they crystallized, versus weakly deformed dikes crystallized at 2.4 MA. In comparison, from the Goodenough dome in the west, we see more of a smear of dates from a whole bunch of samples, anywhere from almost 5 MA down to 1.8 MA for some of these non-deformed plutons that are the red bodies in the core of the dome. And again, just to give visuals for this, the really strongly deformed leucozones crystallized from 4.6 to 4.2 MA, versus it was another 2 million years later where some of these smaller dikes were intruded in place and crystallized. And so putting this all together in a timeline where we have it for kind of all three of the domes that we studied, where in the gray box on the left is the timing of the UHP metamorphism, and then the lighter, brighter gray in the right is when we know that these domes were in place within the shallow crust based on some thermochronology data from Paul Fitzgerald. We can kind of add in information in between this to track that exhumation history, where the retrogressed eclogites and strongly deformed dikes are crystallizing, from about 5 down to 3 MA, in the weakly deformed dikes between 3 and 2, and then the plutons and non-deformed dikes at around 1.8 MA. And so in terms of what drove the exhumation of these rocks, remember, we're in this very active tectonic setting. We're now going to go to a cartoon model that's looking down the axis of the rift and looking towards the west. And so here we are looking towards the west. And what we think happened is that seafloor spreading began at around 6 MA. And this spreading and rifting and this associated asthenospheric inflow likely brought in a lot of heat and caused recrystallization of this continental material and subducted material that had been sitting at these mantle depths. And so that's what likely triggered the timing and the recrystallization of these rocks at the UHP conditions. But it also caused these rocks to become unstable. And so we think from there, they rose up as these little diapirs that eventually come up to the surface and form kind of these domes that we now see today across the islands. And so just to step through time, these rocks were at UHP depths at 5.2 MA. They would have buoyantly risen up to around the base of the crust where they likely achieved neutral buoyancy. And so this early exhumation is recorded by those zircons that had the nanogranite inclusions. So this is occurring around 4.6 MA. And then when these rocks likely stalled at the base of the crust, that allowed some of these melt generations to start to crystallize. And so we think the stalling and likely ponding at the base of the crust occurred from 3.9 to 3 MA based on when the strongly deformed leucosomes crystallized. This is also the time where these rocks likely underwent a large degree of retrogression. And so our peak eclogite facies assemblage is breaking down into things like amphibole as well as plagioclase. We also think this was a time where a lot of the fabrics that are observed across the dome were likely became part of the rocks. And here's work from Tim Little et al. And showing his foliations as well as lineation measurements, and that most of them are in this kind of east-west direction, which is the opposite of their overall plate motion vectors. So this is east-west is recording kind of the direction of the ponding throughout during this time. And this ponding likely lasted for about 1 million years. And we think that the weakly deformed dikes are kind of recording the end stages of that ponding. And so it lasted until about 2.4 MA. And then these rocks were emplaced within the shallow crust by about 1.8 MA based on when we have these non-deformed plutons intruding into the domes. And so we can put together this timeline of everything happening within about 3 million years of these rocks being at mantle depths till 5.2, then ponding at the base of the crust from 4.5 to 3 MA, and lasting at that ponding stage for about 1 million years before being placed within the shallow crust by about 2 MA. So really exciting history for these ultra high pressure rocks. And then just to give you a sense of what's happening today, turn to some of my collaborators' work. And Laura Wallace was doing a big geodetic campaign within this area at the same time we were working within the domes. And so showing the locations where she had her different GPS sites on both the D'Entrecasteaux Islands, as well as the mainland and the Trobriand Islands in the north. And what she saw in her data that was published in 2014 is that clear counterclockwise rotation of the Woodlark Plate. And when she looked at how the extension was being budgeted, most of it is being shared between structures within the Goodenough Bay that's in between the islands and the mainland, as well as those high angle normal faults and various structures within the D'Entrecasteaux Islands themselves. And so really arguing for lots of extension still happening within this area where the UHP terrain is exposed. And then highlighting some of Jeff Aber's work and his former student, Zach Eiland, who looked at what was happening within the mantle and shear wave splitting results. And what they found is that you have this really kind of dominant north-south direction for the shear wave splitting, and really argued that it's mimicking what's happening in that geodetic data. And so you see lots of evidence for extension in the mantle as well as up at the surface. So again, just this really major extensional system that's causing a lot of uplift and exhumation within this area. So if we just wait another few million years or so, maybe we'll have another dome of ultra high pressure rocks exposed to the west here. So just to summarize, we have UHP metamorphism. These rocks were at great depths at 5.2 MA. The eclogites, as well as these multiple melt generations, really capture the retrogression, the partial melting, and the rapid exhumation of these path of these rocks, where they made it up to the surface in 3 million years. But we can break that exhumation into kind of 3 different stages of the mantle to the base of the crust in 1 million years, storage in that lower crust for 1 to 2 million years, and then final emplacement into the lower crust less than 1 million years later. And so overall, the Papua New Guinea ultra high pressure terrane is the only known UHP terrane that's still actively exhuming. And we can really document that in pretty much any geologic technique that you study in that area. And we do think that the buoyancy induced by all these different generations of melt, as well as being within this active extensional environment, is what really drove the really rapid exhumation of these rocks. And so they're exhuming at rates of around 20 to 30 millimeters per year. And so that's all I have for you today. But before I close, just really need to acknowledge the local people on the islands who helped us to do this work. These men were incredible and guided us up the rivers, which is where we collected pretty much all of the samples, because that's the only place where you can actually find rocks exposed. But these rivers were quite slippery. and these guys, you know, even allowed us to just step on their feet so that we wouldn't slip into the water at times. They carried all of our rock samples. We tried to explain some of the geology to them, but they're the people that really made this work happen. So need to throw a little shout out to them. So thank you for your time, and I'd be happy to answer any questions. Thanks.
Stacia, thank you so much. That was incredibly data rich and so interesting. And it's echoed in some of the comments and questions coming through in the Q&A. So thank you very much. And it certainly looks like a very wet place to do fieldwork and humans.
Yes.
So we've got a comment and a question from Lou Ashwell, who says, very nice talk, thanks. How come no pseudotachylites? Many high pressure terranes contain quite thick ones.
That's a good question. You know, part of me wonders if they do exist within the UHP terrane, and part of what's quite tricky is you do have limited access to the rocks because it is in the tropics. And so a lot of, you know, we're only working up these river valleys as well as the coastlines. So my guess is that we're actually missing them and that there are some available. Because I agree, it would make sense for them to be present here, as was pointed out in a lot of the other UHP terranes.
Okay, great. Just to remind the audience, if you do have a question, you can either just raise your hand with that little hand button at the bottom of your screen, or you can type a question into the Q&A box like you did. While we're waiting for some more questions, Stacia, I have maybe a very general question, maybe it's a silly question, but are the processes you're talking about here similar or the same as, I guess, a fairly recent idea on relamination that people like Brad Hacker have been talking about? Is this a similar process, or is it something that runs in parallel to relamination?
I think it is pretty similar. My understanding of relamination is that I think people assume that you have the subducting plate and sediment diappears, or sediment is rising off of that plate and directly underplating the overriding plate. In this case, what's a bit puzzling here is it almost seems like the crustal material may have been stalled in the mantle for a while, where the evidence we have of these rocks being subducted is back in kind of the late Oligocene into early Miocene times. And then there's kind of a gap in time until the rocks recrystallized at the UHP conditions at 5 MA or so. And so we don't really know why or how they could be stalled like that. And so that's where there might be kind of a bit of a more gap in time compared to, I think, what most people assume for relamination.
Okay. Where do you, out of interest,
but a similar idea.
Where do you get the information that they were subducted much before that? Is that from like cores and zircons, or?
Mainly, yeah, it's looking at the detrital zircons within the quartz of feldspathic gneisses, where they do seem to be closely associated with the what's known as the Wits Sunday volcanic terrain that's exposed in northeastern Australia. And kind of what we know about those sediments and when they got translated to the north and likely subducted was earlier. But to be honest, it's like knowing how active this tectonic area is and how many microplates are forming and developing, and people arguing about what's an active trench or not. There could have been an entire different microplate within there that's been consumed that we have no record of at this point. So it's a bit of a mystery what was happening in that time period from around 22 down to 5 MA.
Okay, that's really fascinating. We've got a hand up from Nonku Selo. Nonku, I'm going to allow you to talk. You just have to unmute yourself.
Okay, can you hear me now?
You can, go for it.
Yes, okay, thank you so much for the great talk. This was very nice and interesting. So I'm keen to know about the pressure. Is it like the peak pressure or is it the minimum estimate? Because I see that your temperature is also increasing. So I was wondering if the pressure is the maximum pressure that the rock has seen, or is it just the minimum estimate?
We think it's the peak pressure. I mean, as the best that we can in terms of what we know about the mineral chemistry and doing the forward equilibrium modeling with different thermodynamic software packages. We also did some classic kind of exchange reaction for pressures too, and got similar results. So we think those are likely the peak pressures. In terms of the temperatures, it seems to be a common feature in these ultra high pressure terrains that you do have a bit of an increase in the temperature along the exhumation path. In this case, I wonder if they're being heated up a bit by translating or moving through the mantle wedge, and that's what's causing some of the heating and the temperature increases that are recorded in those zircons that are crystallizing during exhumation. And so that's kind of my best guess to what's happening there. Of course, if we added uncertainties onto here, we probably need to add at least a couple of kilobars. And same with temperatures of probably at least 50 degrees at a minimum onto the temperatures, and so then you can kind of start to shift things around a bit more too in terms of those PT estimates.
Okay, thank you so much. Because usually when you use the mineral chemistry, people, they just guess as a minimum pressure, not the maximum, simply because the mineralogy has been equilibrated. So they can't use the mineral chemistry to precisely estimate the peak pressure. I was just keen to know. Thank you.
I see. Yeah. And we haven't seen any evidence of things like diamond or that sort of thing in these rocks. And so it does seem like they were just within, not just because they're still at very high pressures, but within the coesite stability field. So yeah, you could argue for slightly higher pressures too.
Yes. Okay. Thanks. Great work, by the way. Thank you so much.
Thank you.
Okay, fantastic. Do we have any more questions? You just need to simply raise your hand. But I think it looks like we've exhausted the questions. So Stacia, thank you again very much. I'll just say to the audience, if anyone does want to stay behind backstage and have a chat with Stacia, she has a little bit of time. So all you need to do in that case is just raise your hand and we'll promote you to a panelist and we can have a bit of networking after the talk. But otherwise, we will see you next week. I'm still finalizing the talk for next week. And so you'll get an email on Monday about that. But thank you for joining us. And thank you to John Hancock's and CCIC Group for sponsoring these Geotalks as well. And thank you, Stacia, for waking up early, especially to do this talk. Much appreciated.
Yeah, thanks for having me. It was a lot of fun.